we have to take these equations and the computer can integrate them, right? But we, if it's possible to integrate it, we would like to integrate it and see the end result, because we can learn a lot from that. How the circle comes about, all of that is from the integration of these equations. So we are introducing two new variables. So we have psi I dot, right? And I said that if you integrate it, you get the position. And I also said that computers most of the time numerically integrate it. But we are about to integrate and get a result. Because for the differentially steered vehicle, with certain assumptions, it is possible to get what we call a closed form result. So that's what we're going to do. And we just introduced two new variables. So you don't know it because you don't have that much experience, but one stands for the rate at which, so phi1 dot stands for the rate at which the right wheel, one is right, the right wheel is spinning. This is not a minus sign, it's a dash. And phi2 dot is the rate at which the left wheel is spinning. So how do I go from V omega to phi1 dot and phi2 dot? We'll see. So a better picture of the differentially steered architecture without the caster wheel. So V of t. So by the way, somewhere here, see right here, not on the ground, but between the two wheels is the reference point. That's where the robot's axis is going to be attached, because that's the point of pivot. So that's the best place to put the robot axis. So 2L is the spacing between the wheels. The reason you use 2L and not L is because half of that is the spacing from P to the wheel. That's why you say that this is 2L. So P is halfway between the wheels. So somewhere here. So that's the forward velocity and this is the rotation. However, we don't have motors directly giving V and omega. We have motor here and a motor here. So if you want to design the controller, then you have to get down lower than V omega, because V omega is for your convenience. So notice the wheel radius. This is important. The spin. Motors typically rotate the wheel. That rotation is equal to a certain amount of tire being laid out, right? You know the rule, right? R phi1 dot, right, is the amount of tire that's rolled out in a second. Do you remember that from some previous math class? So we will use that. Okay. Now I'm not going to use this derivation. That's why I've got a note saying I don't like this derivation really. I have a separate sheet and that's already uploaded. So the left wheel is here, the right wheel is here. L is the spacing from the left wheel to the midpoint of the axle. L from the midpoint to the right wheel. The right wheel is 1, the left wheel is 2. So let's say that you fix the velocity and you move forward, right? That means fix the velocity means what? V is fixed. In order for V to be fixed, these two velocities should be also fixed. And then I roll a little bit. So I roll just a little bit because you know how calculus works, right? You do an incremental thing and dt's and all come in. And then that result can be generalized. You know, this is the beauty of calculus. Isaac Newton came up with calculus. So what happens is, if you move for a short interval of time dt, and the left wheel has a velocity v2. Now what is the velocity of the left wheel? So the velocity of the left wheel is, if you take the middle of the wheel, what is the velocity with which it's going forward? Similarly the right wheel, the middle, you know, that's the wheel, the midpoint of the wheel, right? Now, we'll get to that, you know. So do you agree that V2 dt will be the amount of tire that rolls out? So if the right wheel is going at a certain velocity, the amount of tire that will roll out is V2 dt, and I'm calling that dS2. Calculus terminology, a tiny increment. And And the right wheel similarly ds1 is v dt. Is that okay? What about the midpoint? The midpoint is ds is equal to v dt. V is the velocity of the robot. That's the velocity of the midpoint of the robot, right? You can use that as a reference point. It's moving forward by v dt in time dt. It moves forward by v dt equals ds. So ds2 is v2 dt, ds1 is v1 dt, and the midpoint is v dt. Is everyone okay with that? Also, let's identify some other pieces of terminology. So when you lock the velocities, there is an instantaneous center of rotation. So you're moving around the circle, right? The center of the circle is out there somewhere. If you're going more straight, that center will go further because your radius is larger. Remember the straight line? What is the radius of a straight line? Infinity, right? Where is the center? It's disappeared, right? So that's the concept of this ICR. It's the instantaneous center of rotation. So as you change the curvature, this ICR location goes in and out, and it may actually go on the other side because when you turn this way, if your circle is this way, the instantaneous center of rotation is out here. So it's very dynamic. And this is the radius of curvature from here to the midpoint. See, this is R. So the left wheel is at a distance of R minus L from ICR. The right wheel is at a distance of R plus L from ICR. Okay, let's get into the equations. So V1, the velocity of the right wheel, remember I asked you this a few minutes ago, R, the radius of the tire, times phi1 dot. Phi1 dot is the rate at which the right wheel is spinning. What are the units of phi1 dot? Anybody? Radians per second. So motor shaft, a motor connected there will spin it, right? Motor output is radians per second, right? It's omega. So if you directly couple it, you can use gearing or whatever. Doesn't matter. It's going to give the right wheel a radians per second. Similarly, left motor, radians per second. Do we have a steering wheel on a differentially steered vehicle? Do we have a steering wheel on a differentially steered vehicle? No. So there are wheelchairs. I'm telling you that this one doesn't have a steering wheel. So we have wheelchairs with a handlebar, just like a bike. So that has a steering wheel. It's a different robot. This one has no steering wheel. You just have to make the right wheel go faster than the left wheel. Okay, so everybody gets this? V1 is equal to R phi1 dot. And V2, remember, you don't know this because you haven't worked on this enough. 1 is right wheel, 2 is left wheel. So V2 is R phi2 dot, right? And ds1, the amount by which the wheel rolls out is V1 times dt. So R phi1 dot dt. Are you with me so far?
Yeah.
And ds2 is V2 dt is equal to R phi2 dot dt. So what do you think the midpoint is going to be? It's going to be the average of the two. If you found how much the left wheel has rolled out in time dt and how much the right wheel has rolled out in time dt, then the midpoint, you take the average of the two. Here it is. Right? So I can take dt and move it to this side. And v is equal to ds by dt will be the velocity, right? And here's your first equation. R phi1 dot plus R phi2 dot by 2 is equal to v. So your forward velocity is going to be controlled by the rate at which you spin the two wheels. So you were kept away from that because to control a robot you just need V and omega. But anybody designing the robot or designing its controller has to know this equation because this is what connects to the motors. Alright, so now having got one equation which is V equals R phi1 dot plus phi2 by 2, we also need an equation for omega. So to do that, he says take equation 3 and 4, this one, and do something with it. ds1 is equal to R phi1 dot dt. And this is the extended form. See, I took this equation. Wait a minute, where did he get that from? He says ds1 is not only R phi1 dot dt, but it's R plus L theta dot dt. Let's go back and look. This angle, right? See, you moved through a certain angle, right? But remember, you're only moving for dt. So theta dot is a rate. So to get the actual angle, you have to multiply by dt, right? Theta dot is no different from omega, right? Remember, it's another name for omega. So he says, if I take r plus l and move it through theta dot dt, should I get ds1 also? Similarly, if I take r minus l, which is small l, but we don't need small l, r minus l, right? And I move it through this angle, should I get ds2? And that's basically what the extension is here. Are you all with me?
Yes.
Now, from these two equations, I subtract the second equation to the first. Don't worry about, this. It's r phi 2 dot minus r phi 1 dot. No, it's the other way around. R phi 1 dot dt minus this, right? And on the right hand side, you will have the r's cancelling out. Do you see this? R theta dot t, r theta dot t will cancel out, and you'll get this. Is it okay? Subtracting 8 from 7. I solve for theta dot. Theta dot is equal to all of this divided by 2l dt. Dt cancels.
Yeah.
And there's your second equation. Omega. Remember V and omega control the robot? Well, V happens to be r phi 1 dot and r phi 2 dot by 2. And omega happens to be r phi 1 dot minus r phi 2 dot, but also a 2l here. So only a 2 there. 2l here. Plus that. Minus here. So you have your two equations for V and omega. These are the real motors. Phi 1 dot, phi 2 dot are the real motors. But a roboticist does not have to know that. You just keep giving V and omega, and the controller will figure out how to take the V and omega. So by the way, do you realize this? Given phi 1 dot and phi 2 dot, I can calculate V, right? I can also calculate omega. But do you also know that I can go the other way around? Given V and omega, I can use these two equations to solve for phi 1 dot and phi 2 dot. So it works both ways. It's a simple linear equation, simultaneous linear equation. Do you get that? I can, given V and omega, so the roboticist will say V omega. But if I solve that, I can figure out phi 1 dot and phi 2 dot. And it is the job of the controller to create the phi 1 dot and phi 2 dot that gives you the desired V and omega. That's not the roboticist's job. That's the controller takes care of that. Is that okay?
Yeah.
So, if there is a maximum limit on the V, where is it going to come from? It doesn't come from V itself. It comes from the limitations on phi 1 dot and phi 2 dot. Maybe your motors cannot go to that high rate, right? So those are electrical engineering limitations. The fact that the robot cannot go above a certain V is because of the limitations on the motors. Nothing to do with V. V is obtained from phi 1 dot and phi 2 dot. Similarly, if it can't turn that fast, it's because it's limited here and here. Also, from the figure, there's one more angle thing that we did not do. Look at this. This is R, right? Isn't R times theta dot dt equal to this R here? We did it for the left wheel and the right wheel, but what about R times theta dot dt? Isn't that this R?
Yeah.
Here it is. And there's your equation. See, R theta dot dt is equal to R omega dt is equal to V dt, all from that figure. And then R turns out to be just V by omega. Is that okay? Because take this, dt cancels, V by omega gives you R. So that's how we got the equation for the radius for a differentially steered vehicle. This is only true for this differentially steered vehicle, but all robots will follow this principle, that if you lock the speed and you keep the steering wheel for a car like this, you'll go in a circle. So that basic principle is true generally. Here we have derived it only for the differentially steered vehicle. Okay, let's go back and finish up with that Professor Chris Clark's, this one. So I don't like his explanation, that's why I went with my own. It's fine. But a lot of explanation, I thought my explanation was shorter. He does it over many slides. I don't like his approach. Okay, here. So this is what we derived earlier. Remember this? So this is the expanded equation where we don't take out, see 0 here all the time. So if you're having 0 here all the time, there's no need to use this at all. Because it's a waste, right? But now he's gone back to the full form. And then he says that why not take this V and omega. Now by the way, this is your R theta inverse. If you wondered, remember that transformation matrix? This is it, all of this. So notice something, it's a very heavy job for the integrator, the numerical integrator, because theta I dot, right? I said if you integrate it, you can figure out where the robot is. The car driving from Chennai to Vellore, you can figure out on a map, on a global map, not a local map, because then somebody sitting on a different frame won't understand what's going on. So even if there's a second robot, maybe your friend is driving in a different car, he should see it on the global frame. Then he'll understand your progress, where you are, right? So similarly, if you look at this, when you integrate it, it's a lot of work. You know what makes it a lot of work? It's because this angle is changing all the time. You're not just fixing a heading and driving on that as a straight line. Then cosine theta is a constant. The theta is changing all the time. So that's why a computer has to do a lot of work doing the numerical integration, because the theta is changing all the time. It's dynamically changing. It's a robot, right? It's not a fixed frame. So it's changing all the time. So now we replace the V and omega, and he leaves the 0 in here, but because the side velocity is 0. But this is the equation, the kinematic equation. Let me pull it down. In my MATLAB, okay, I don't need this. See, they have a bicycle model also, which I was playing with. So MATLAB has these equations implemented, the kinematic equations. We are going to, this afternoon, do it with the help of the gazebo robot, which is real. The MATLAB robot is a kinematic version of the robot, so it's not real. The gazebo robot has kinematics and dynamics built into it. But this helps you learn. So the reference is right here. The usual cleanup, you know. So this kinematic model, so this is an object, you can get a copy of it, you know, kinematic model. So this is an object and you get a copy of it, the kinematic model. I define the initial state, which means it's starting from 0, 0, 0. And then the time span of simulation, so I say I go from 0 to 1.5 pi. You may ask, why is he doing this? Why not give me a time and number as a number? Because this turns out to be a fraction of a circumference, that's why. Because you know, you'll get 2 pi r for a circumference, so if you put in time this way, the pi cancels and it, you know, you get a nice result, that's all, you know, no mystery. So T-span is 0 to 1.5 pi in increments of 0.05. You know, I just picked 0.05 because you like the plot to be, you know, close, otherwise it look odd. So by trial and error, you can make it smaller or larger. So by taking the kinematic model, so I've got a copy of the object, and by taking it and this extension, by setting it to this reserved word, I'm saying I want to command it by using V and omega. There is also a way of commanding it by saying I want my right wheel to spin at this rate and the left wheel to spin at this rate, right? But I want to be a roboticist now. I don't want to bother about, you know, individual wheel speeds. So I want to tell it V and omega and show me the path. So these are the two inputs, which means that the forward velocity is 1.5 meters per second and the turn rate is 1 radian per second. So this is a software object. So you can make this move forward at 500 miles per hour. Nothing will happen. This is a MATLAB. It's just implementing those equations. It can go as fast as you want it to go. It will be fine. The gazebo robot is different. Those are meant to be simulations of real robots. So if they have put those features in, you'll find it doing strange things. It might even topple over. And then I'm plotting the y, one of those coordinates with, because the result comes out in y. You know, this is all in the help file. See? Oh, by the way, look at this. I provide the inputs, right? And you know what ODE 45 and this derivative means? Because I told you, even if you have a result in the form of an equation, MATLAB and all simulators will always integrate it numerically. They just, because the number of cases where you can find an integral result is very few, so they say I'm going to integrate anything, even if it's available. By the way, if I change the circle by changing these numbers here, if I say, okay, change it and now run it again, obviously, it's better to numerically integrate it. And what if I change it point to point? I'll get a very fancy path, right? Won't I? So then you have to numerically integrate. You can't use the equations anymore. Equations are nice for a general understanding, but it's better to differentiate it and let MATLAB integrate it. So that's what is happening here. It's taking the derivative of the kinematic model. It's what we derive. And then it's giving you the result, t versus y. Y contains both the x and y coordinates. It's not giving you the heading. If you want the heading, you have to do a little bit more work because that's a third variable, the orientation, right? But if you plot x and y, you can figure out the heading, isn't it? If I told you the car is here, 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 can't you figure out the heading? You can figure out the heading automatically. So it's ready to run, and you can play with it later during the afternoon session. And I've got the plot here. Now you can figure out why I'm only getting 3/4 of a circle, right? 3/4 of a circle, do you agree? Let's see. I'm simulating for 1.5 pi, right? So ask yourself, how long will it take for this robot to go a full circle? First of all, what is the radius? So here are my speeds. Where is it? Here's my speed, right? Radius is 1.5, right? 2 pi times the radius gives me the whole thing, right?
Yeah.
So what is 1.5? It's 3/4, isn't it?
Yeah.
How do I get a full circle? Let me simulate for a little bit longer. Where is mine? Okay. 2? Did that work? That's right. I think it's working. So that's why I use the pi, because the pi cancels. So now I'm going to let you think about an exercise over lunch, but maybe don't think about it because you want to relax over lunch. Depends on how good the food is, right? If the food is lousy, then you start thinking. But what if I change the V and omega, instead of letting it go this way, what if I change the V and omega? Find a way of running that MATLAB program by giving it an array of values, V omega. So you can say for 0.2 seconds, use this V and omega. After that, change it to a different V and omega. You should be able to do curved paths of different kinds. So different tiny circles, right? How do you go from this to this? Well, let's see. Here, minus. Is it okay? I made omega minus 1 radian per second. Now, of course, it's still going to look the same because the circle is. So what I'll do is I'll go back to plotting part of it. Then perhaps it'll make a difference. It's 1.5, and this is what I get. Does this make sense? 0. I started at 0, 0, right? So that I started here. See, I started here. So it's going the other way. Do you get it? Remember the initial state? The initial state was somewhere here. I put 0, 0. Here, 0, 0, 0. So I started here. I went the other way. See, 0, 0 is here. 0, 0, right? How about if I put it in a different initial state? I want to change this. I believe this cannot be in degrees. Third one is what? Theta. It cannot be in degrees. Let's make it pi over 4. 45 degrees. So So I still started at 0, 0. 0 and 0. But it was pointed in this direction. Got it? It's still doing the same fraction of the circle, right? But we put it on a different orientation. So that program is available. You should be able to run it. Now, if you think that this does not look like a circle, it's because we have to use the equalize axis feature of plot. Because right now it's not using the same scaling factor, and that's why it looks like an egg. It's really a circle.